Algebra, Chapter 4, Section 4, Scientific Notation. Starting off with our vocabulary here, so standard form are numbers that do not contain exponents, for instance, 2,000 or 3,840,000,000,000. Scientific notation is a number that is expressed as a product of a factor and the power of 10. For instance, 2,000 can be written as 2 times 10 to the third, because we move that decimal from the end and we move it 3 places to the left. So the 3 is positive because it would take positive 3 direction, so to the right, to get back to that original number. So then when we move over to this 3,840,000,000,000, we move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 places. And to move it back to the original standard form, the expanded form, we have to move it to the right. So again, the 12 is positive. We take the decimal and we always put it between the first 2 significant digits. That way we have only a number in the ones place, and then we have decimals. So one place and decimals, that's all we are looking for. We don't want anything in the tens or the hundreds. We just want that first ones place. Our quick check here for what we have done before: find each product or quotient expressed using exponents. So 10 to the 8th times 10 to the 4th means that we will have 10 to the 8th plus 4 because we're multiplying, so we add those exponents. We get 10 to the 12th. A to the 5th times A to the 5th means we get A to the 5th plus 5th, so A to the 10th. A to the 6th divided by 8 to the 2nd, so we're dividing, which means we subtract those exponents because, again, subtraction gets smaller, just like division. So we get 8 to the 4th. If we had to, we said with exponents, we don't have to expand that answer out. X to the 9th divided by x to the 3rd, again, that gives you x to the 9th minus the 3rd, so x to the 6th. 4y times 5y to the 4th. We first do the coefficients out front. 4 times 5 is 20, and then it's y to the 1st plus 4, so we get 20y to the 5th. In the metric system, 1 kiloliter is equal to 10 to the 3rd liters. So 1 kiloliter is equal to 10 to the 3rd liters. 1 liter is equal to 10 to the 3rd milliliters. How many milliliters are in 1 kiloliter? Okay, so that will be 10 to the 3rd times 10 to the 3rd, so we'll get 10 to the 6th, which means that there's 6 zeros on it, so it will be A. There are 1 million kiloliters. There's 1 million milliliters in a kiloliter. Okay, so essential question: why is it useful to write numbers in different ways? Well, we're going to learn today how to shorten everything to where you don't have to write out huge numbers like we talked about in the vocabulary. What will we learn? We will express numbers in standard form and in scientific notation, and then we will compare and order numbers written in scientific notation. Express each number in standard form, moving the decimal, so it starts out 2 decimal. It's an unseen decimal. You put it in, it's always to the right of that whole number. And we move it the number of times that we have an exponent. So 3, 2,000. 6.8 times 10 to the 5th. The decimal is shown, so all we have to do is move it to the right 5 times. We have one number here with the 8, which we keep, and then we have to add in 4 more zeros to get 680,000. 3.25 times 10 to the negative 4th. So far, all we've talked about are those positive exponents. The positive exponent means what it takes to get it to expanded form. And it means that you move it to the right because the answer is, or the exponent is positive, and the positive direction is to the right. So to use it is to move to the right. Well, if you have a negative exponent, To use it means you move to the left to get to expanded form. Whenever you're deciding whether you need to use a positive or a negative exponent, it's always helpful to think, well, I was in standard form, how do I get back there? And that's what your exponent will be, whether it be positive or negative. So in this case, because it's a -4, we're going to move it 4 places to the right, 1, 2, 3, 4. So we have 1, 3, and then we have to add in 3 zeros, a decimal, and of course we want a 0 in the ones place. So we have 0.000325 as our answer there. To try some on our own, 3 times 10 to the 5th. So our decimal starts here to the right of the 3. We have a +5. Positive means we move to the right. We move to the right, 1, 2, 3, 4, 5, and we add in our zeros. We write it 1, 2, 3, 4, 5, and I put in the comma. So you do need to rewrite it with your comma. We have a +4 here, so I'm just going to go ahead and write a number. And since it's a +4, we move to the right to expand it. 1, 2, 3, 4. Add in 1 0. So 4, 3, 9, 5, 0, 1, 2, 3. There's my comma. So these are the answers that I want to see without the moving of the decimal. We have a -6 here, which tells me, because it's negative, it's to the left to put it in expanded form. So we have 6.79, and then move to the left 1. And then I'm going to add 5 more zeros. 1, 2, 3, 4, 5. My decimal and the 0. So it's 0.1, 2, 3, 4, 5, 6, 7, 9. And of course, we don't put decimals in, or we don't put commas in the decimal part of our number. Express each number in scientific notation. That means we need to move the decimal between the first 2 significant digits, so we end up with a number in the ones place. The decimal starts at the end, and we move 1, 2, 3, 4, 5, 6 places. So 4 times 10 to the, and that's where you have to think about, well, to get back to that standard form, I would need to move my number to the right to get back to 4 millionths. It has to be a +6 because we would need to move to the right. Okay, on 2, we take our decimal and we move it between the 7 and the 2 because that's the first 2 significant digits. It gives us a 7 that is in the ones place, and only the ones place. So 7.2 times 10 to the, well, what's it take to get back to the number we started with, the standard form? We move to the left, which means to move to the left would be a negative. So 7.2 times 10 to the -2nd. Express each number in scientific notation. So I'm going to start my decimal at the end since it's not shown. I'm going to go 1, 2, 3, 4, 5 places. So 8 in my ones place, 0.0 times 10 to the, and because I would need to move to the right to put it back into that big number, to the 5th. I move my decimal here 2 places till I get a 1 spot with a number in it. So I have 1.19. I move 2 places, so times 10 to the, and to get back to the original number, I would have to go to the left, which tells me it's negative because left is negative. So 1.19 times 10 to the -2nd. The population of Kansas is 2,853,118 people. Write an estimation in scientific notation for the population. Well, 2.8 million, really close to 3 million. So they wrote it here as 3 million in the estimate. And then they said, well, you can move your decimal to the left 6 places to get 3 in the 1 spot. So 3 times 10 to the, and to get it back, you would have to move it to the right, so that's a +6. So the population of Kansas is about 3 times 10 to the 6 million people. But that saved us some space by putting it in scientific notation, which is the whole point behind scientific notation. The space shuttle traveled at about 8 kilometers per second. Hold on, I may have missed one. There we go. The population of Montana is 998,000. 998,199. Write an estimation in scientific notation for the population. 998,199 is approximately 1 million. I'm going to move our decimal 6 places. So we get 1 times 10 to the, and since we moved it to left to get it back to standard, we have to move to the right. I'm going to put in a positive 6 here. The space shuttle travels at about 8 kilometers per second. At this rate, the shuttle would take about 4.5 times 10 to the 4th seconds to fly to the moon. Is it more appropriate for a newspaper to report this time as about 4.5 times 10 to the 4th seconds, or about 12.5 hours? Explain your reasoning. It would be more appropriate to talk about hours, because when you talk about seconds, people think of seconds as being really fast, when in reality you have so many seconds that it takes hours. And so your non-scientific people, you need to use their language in order to make sure that they understand what's really going on. So you would use hours because it's more appropriate. So the number 4.5 times 10 to the 4th seconds is very large. So choosing the larger unit of measure is more meaningful to those people, especially outside of the scientific community. Inside the scientific community, they would automatically change it over and go that this is a lot of time. But to your non-scientific person, they would think of it as being a very short amount of time because the units are misleading here, saying that it's in seconds. If you could ride your bike 200 meters per second, it would take about 1.92 times 10 to the seconds to ride to the moon. Is it more appropriate to report this time as 1.92 to 10 seconds or 22.2 days? Days is more appropriate unit, as we are talking about a large number. The table shows different geologic time periods. Order the time periods from oldest to youngest. So from oldest to youngest, the first thing that I want to look at is my exponent. So my largest exponent is going to be those 8s. After that, so it did say from oldest to youngest, so the oldest is the larger exponents. Then we look at our numbers. So we have 2.08, 4.38, 2.45. Now we need to order them. The largest ones place is going to be the 4.38. So the Silurian is going to be the largest. It's going to be the oldest. From there, we have to look at the tens place, and the Triassic is the bigger number, so it's older than the Jurassic, which leaves the Tertiary as the youngest. Okay. So the time periods ordered from oldest to youngest are Silurian, Triassic, Jurassic, and Tertiary. The diameters of Neptune, Saturn, and Uranus are 4.9 times 10 to the 4th, so that's Neptune, kilometers, 1.2 times 10 to the 5th, that's Saturn, and 5.1 times 10 to the 4th, Uranus, respectively. So order the planets from greatest to least. So first we start with the exponents. So the largest exponent is here on Saturn, so we have Saturn. Then we look at the other two. So the larger, we said from greatest to least, yeah, the largest is right here with Uranus, and then we have, and so lastly would be Neptune. Our vocabulary that we talked about at the beginning, again, standard form is that expanded form, that larger form, all the numbers. Scientific notation is whenever you put the decimal between the first two significant digits, and it's multiplied times the power of 10. Our key concept in scientific notation, so words. A number is expressed in scientific notation when it's written as the product of a factor and a power of 10. The factor must be greater than or equal to 1 and less than 10. So between the first two significant digits, so we have a number in the ones place. So that's why we have 3.5. We have 3 in the ones place. And then our other significant digit is 5. If we had had a 1 right here, we would have had to have taken this to 3.501 and left off the other zeros. It's not what we had, but I just wanted you to be aware of it. And if we have to move to the left to get back to our standard notation, our expanded form, that means we're going to have a negative exponent there. So why is it useful to write numbers in different ways? It makes it quicker to get everything written down, so especially if you're doing a scientific paper or you're giving out a scientific answer, it is a shorthand version. So write about how learning about negative exponents helped you with scientific notation. So include reasons why negative exponents and scientific notations might be useful in the real world.